So this video is going to deal with the transfer of strength and power adaptation to sports performance, horizontal and vertical force production. And this is a paper that you needed to read for the linear kinetics part of the biomechanics course. And basically I just want to highlight the main purpose of this paper. And one is to try to change our approach in gym-based strength gains that could be improved if exercises involved both vertical and horizontal force production. Typically we're doing box jumps, any sort of vertical plyometrics, and that is focusing on vertical. But dealing with running velocity, which takes us back to an earlier concept, you can increase velocity by increasing the stride length and the stride rate, because velocity is equal to stride rate times stride length. All right, so we could do one or both. Then the initial paragraphs start to say, well, how do we increase that velocity? You increase velocity by increasing impulse, right? Because impulse equals momentum. And impulse is you apply a force times a time on the ground, or a ground reaction force, and it results in a momentum, or a mass times velocity. And here is your velocity component. So, but you can have both a vertical ground reaction force and a horizontal. And if you recall from the lab, the horizontal is the braking force and the propulsion force. And so this paper is just trying to figure out, is direction important, because it's not typically considered? And if so, which one is key to maximizing running velocity? A final consideration for this paper is the difference between, or to compare, max velocity or acceleration. And for certain sports that need to sprint or be fast in short bursts, the argument may be that acceleration is more important than your max velocity. And so we'll be dealing with that later in the paper. So I gave you a series of questions to consider while reading this paper. And one was, let me go back to here, was that figure 1, and I'm going to expand it here. Figure 1 connects many concepts that we've covered in this course so far, and I think this is a good way to study, right? So you can go, and we know that velocity is stride length times stride frequency, right? We discussed that in the running kinematics portion. Then you can get into what increases stride length: takeoff distance, flight distance, landing distance, which gets into things that affect basically projectile motion, right? Because every step you take, you're basically flying through the air as a projectile. So if you remember, the angle at takeoff, takeoff velocity, and the height of your takeoff affect projectile motion. And then we also remember that air resistance can affect that projectile. Here we're getting into flight time and stance time. And so that gets into stance and swing phases of the gait cycle, right? The braking phase and the propulsion phase, which are the two phases of your vertical ground reaction force that we saw on the Treadmetrics treadmill. And then you could even just say, oh, force. Let's define a force. Let's define velocity. So this is a good way to just kind of review some of the other concepts that we discussed in the course. Let's consider questions 2 and 3. So number 2, in the discussion of stride frequency, the article reviewed the literature and concluded that both fast and slow runners present similar swing times, and thus the differences in stride frequency are based on the stance portion of the stride. Let me get a pen here. So we have the stance portion that seems to be the key feature. So number 3, it goes into increased velocity due to an increased stride frequency may be due to a decrease in time in contact with the ground. So I'm asking you to provide two pieces of data from the studies that support that statement. This statement that decreased stance time or contact time is associated with increased velocity. And I saw 3 papers stated that support that. So this is the end talking about the Numella et al. Paper that related those two things, increased velocity and decreased contact time. We have the Weyand paper here that suggests similar data, and then the Kairalainen paper that also supports this. Right? And always remember when you're reading certain journal articles, like one article or one piece of data does not make the whole story. So it's always nice to have repeatability and things pointing to a similar concept. Question 4. Another approach to increasing velocity is to increase stride length. Was stride length found to be related to an increase in vertical force or horizontal propulsive force? So let me move that. First, let's look at the data that suggests that running velocity and stride length are related. So here we see an increase in running velocity and stride length, the correlation coefficients of 0.66 and 0.73 for 2 studies that were mentioned. So that is a way to increase velocity, which we all kind of knew. So then the question is, was stride length found to be related to that vertical force or the horizontal force? And basically the short answer is both. So I'm going to minimize this, and here we see, we'll maximize this, hopefully I'm not getting you guys seasick, but we have that the in Numella et al. Reported that an increase in stride length was related to an increase in both vertical force with a correlation coefficient of 0.58 and horizontal propulsion force with a correlation coefficient of 0.73. And those are both pretty good correlation coefficients for this type of data. So that is our answer. Both are important. Question 5. The paper provided support that an increase in running velocity was achieved through an increase in vertical ground reaction force. Provide 2 pieces of evidence discussed in the paper to support that theory. So that is basically over here. The Weyand article. As velocity increased, there was a 1.26 times greater vertical ground reaction force for faster runners. Sometimes they also, to compare speed, they did uphill versus downhill, right? Decline running, you tend to go faster than up incline. So that also showed an increased vertical ground reaction force. And then a final paper is Nig et al. Also found as velocity increased from 3 to 6 meters per second that there was an increase in the vertical ground reaction force. And you probably also found this during your lab on the tread metrics. As speed increased, your vertical ground reaction force went up. Question 6. The paper also concluded that horizontal force production is more important than vertical force production for increased velocity. And now we're going to discuss why they concluded that. So first they highlighted the Hunter et al. Paper, which used multiple regression, and they said that the horizontal or propulsion horizontal force explained 57% of the variance in sprint velocity, whereas relative vertical impulse did not explain any further variance in sprint velocity. So within their model, basically the horizontal or the propulsion force explained all the velocity changes, and when they added in vertical, it didn't explain anything above or beyond what the horizontal forces explained, the propulsion forces. And here's some numbers for that. So we have the Monroe article that looked at the relationship between increased velocity, and they found that the propulsive impulse increased as velocity increased by 79%, and the vertical impulse only increased by 21%. So here's the 79%, and as the vertical ground reaction force only increased by 21%. Similar data by Kairalainen also showed that the horizontal increased by 175% and the vertical only by 30%. Again, Brugeli, if I can find, here it is, the Brugeli article had 105% increase in horizontal forces as velocity increased, and only 18% for the vertical forces. Then they broke down the data a little bit more, and a paper by Keller et al. Looked at different speeds, right, from 40 to 65% of max velocity, and then 65 to 100%. So when they were in the 40 to 65% of max velocity, the horizontal forces increased by 38%, the vertical only by 17%. Let me change colors. And then when we went from 65 to 100% of max velocity, the horizontal forces increased again by 48%, but we see that there was only a 1% increase in vertical forces as velocity increased. So in general, horizontal changed more with faster velocities, and it seemed to be that at higher, really fast velocities approaching max, horizontal was a big contributor. So to summarize, based on these data that were presented in this paper, the review of the data, what of these two exercises would you choose for your client athlete? Hopefully you decide on this one, because you have a horizontal component, right, because you're trying to move forward, so your ground reaction force looks something like that. So part of it is going in the horizontal direction, part of it in the vertical. Here in the box jump, most of your ground reaction force, even though it's slightly at an angle, slight bit horizontal, the majority in the vertical direction for these box jumps. So a lot of people do box jumps, but now you have to be creative. How would you change a box jump to increase the horizontal component, this component? Maybe push the box further away, which could lead to some dangerous things. Maybe put a small obstacle so they have to jump over and go forward. So this is now for you to understand the science and then use your creativity in the gym. All right, good luck.